Hello students, in previous video we have seen the examples on Fermat's theorem, Euler's theorem. Now let us start the linear congruences. So let me take the definition of it first, linear congruences. Definition. Let m greater than 0 be a fixed integer, okay, then a congruence of the form Ax congruence to B modulo m, where A, B are what? Integers and x is a variable. Is called a linear congruence modulo m. Linear congruence modulo m. For example, 2x congruence to 3 modulo 5, x congruence to 3 modulo 7 are the linear congruences. Okay. While if I take 2x square congruence to 3 modulo 5 is not a linear congruence. Okay. Now let me take another definition, one more definition. Now it is of the solution of linear congruence. So a solution of a linear congruence Ax congruence to B modulo m is the integer x naught such that Ax naught congruence to B modulo m, which satisfies this, is known as solution of linear congruences. For example, first one, suppose 2x congruence to 3 modulo 5 has x equal to 4 is a solution. As 2 into 4 is equal to what? 8, and 8 congruence to 3 modulo 5. Again, x congruence to 3 modulo 7 have x equal to 3 as a solution. 3 itself is the solution of it. Fine. Now the next one, 2x congruence to 1 modulo 4 has no solution. Why does this? look at here, 2x congruence to 1 modulo 4 means what? 4 divides 2x minus 1, that is 4 divides 2x minus 1. That is same as there exists some integer k such that 2x minus 1 is equal to what? 4k. That is same as 2x is equal to 4k plus 1. So this is what? An even integer. 2 times x will be an even integer. Even integer is not of this form, 4k plus 1. So it is not possible that there exists some k in z such that 2x equal to this, or this is what? X is equal to 4k plus 1 upon what? 2. That is equivalent to 2k plus half. So for any k, this won't be an integer. For k, if k will be an integer, x won't be an integer. What is said here? X is a variable, but which type of variable? It should be an integer. So this is not happened. This does not exist. That's why it doesn't have a solution. Now let us take the theorem for saying about the solution of this one when it has a solution. There is one theorem which says the linear congruence has a solution. When does it possible? So theorem, a linear congruence Ax congruence to 1 modulo m have a solution if and only if a and m are relatively prime. This is the theorem. If and only if means this one will be given, then we have to prove this, and if this is given, we will prove this one. Fine. So proof of it. The same statement can be given in another language. Let me say here or any two solutions are congruent to modulo m. Sorry, it is not or here. It will be an uniqueness property of those solutions, modulo m we can say. Fine. Uniqueness property of them. They are congruent to each other. Any two solutions are congruent to each other, and we can say this part. Fine. Now let us see the proof of it. Now let us assume first this congruence have a solution. So suppose Ax congruence to 1 modulo m have a solution. Has a solution. Say x naught. Let it be x naught. So as its solution will be x naught, so it gives a x naught congruence to what? 1 modulo m. That gives m divides a x naught minus 1. That is same as a x naught minus 1 is equal to m into k, where k is what? An integer. Fine. This is same as to say a x naught plus m into minus k is equal to what? 1. So what does this give? This gives, it is a linear combination of what? A, m and the GCD of them, it is what? 1. So it gives the GCD of a and m is what? 1. Now we have proved the direct part. Now conversely is what? 1, means they are relatively prime. So our claim is that we have to prove that Ax congruence to 1 modulo m have a solution. That thing we have to prove. Fine. Have a solution. Now, as what is with us? This one. The GCD of A and M is what? 1. So, this gives there exists x0, y0 are what? Integers such that what? Ax0 plus my0 equal to what? 1. This gives Ax0 minus 1 is equal to m into what? Minus y0. So, that gives us m divides what? Ax0 minus 1. That is same as Ax0 congruence to what? 1 modulo m. So, this shows this Ax congruence to 1 modulo m has a what? Solution. This shows that x0 is a solution of what? Ax congruence to 1 modulo m. It is a solution of it. Now, we have to prove about this uniqueness part. This is about the theorem we will prove for uniqueness. Now, let x1 and x2 be two distinct solutions of Ax congruence to 1 modulo m. Of Ax congruence to 1 modulo what? M. Now we have to prove that x1, x2 are what? Congruent to each other. If these are the solution, means they satisfies this equation. So it gives Ax1 congruence to 1 modulo m and Ax2 congruence to what? 1 modulo m. That is same as to say Ax1 congruence to 1 modulo m and 1 congruence to Ax2 modulo m. Why does this? A congruence to B modulo m, so B also congruence to A modulo m. Using that property of congruence, we have written this. Now, from this we will get the transitivity. Look at here. First one congruence to 1 modulo m, one congruence to second modulo m. So, first and third are what? Congruent to each other. So, Ax1 congruence to what? Ax2 modulo m. But as we know, A and M are what? Relatively prime. A and M are relatively prime. So, that gives us x1 congruence to what? x2 modulo m. As A and M are what? Relatively prime to each other. This is given to us. Fine. So, what does this shows? These are what? Congruent to each other. So, any two solutions are what? Congruent to each other modulo m. So, this shows that any two distinct solutions of Ax congruence to 1 modulo m are congruent to modulo m. Fine. Now, remember here one thing. If A and M are not relatively prime, then it won't have a solution. It doesn't have a solution. So let me write that part as a note for this. Now, note, if A and M are not relatively prime, then Ax congruence to 1 modulo M have no solution. Have no solution. For example, 4x congruence to 1 modulo 5. Then look at here, 4 and 5 are what? Relatively prime. So it has a solution. Then x equal to 4 is a solution here. X equal to 4 is a solution, and other solutions are what they? 9, 14. If we add 5 in this, each one will be what? A solution. So it has infinitely many solutions. But they are what? They are congruent to each other. They are what? Congruent to each other. Their remainder is always what? 4 modulo 5. That's why they are congruent to each other. Each other modulo 5. While they are different, but the remainder is always what? 4 modulo 5. Fine. Now another note you can say, let it be first. Then second note, if A and M are relatively prime, then by Euler's theorem what can we write? Then by Euler's theorem, we can write A raised to phi of M congruence to what? 1 modulo M. This is Euler's theorem. Now this can be written as A raised to phi of M minus 1 into what? A. A raised to phi of 1 minus M minus 1 into A congruence to what? 1 modulo M. Okay, this can be written as such. Fine. Now what does this say? X equal to what? If we compare with Ax congruence to 1 modulo M, so x equal to what? A raised to phi of M minus 1 is a solution of what? Ax congruence to 1 modulo M. Okay. For example, the solution of 3x congruence to 1 modulo 20 is what? 3 raised to phi of 20 minus 1. That is 3 raised to what? 8 minus 1. That is what? 3 raised to 7. 3 raised to 7 is a solution of this one, modulo M. Fine. This is about these nodes. Now let me take one small lemma. That if P is a prime, then x square congruence to 1 modulo P, if and only if either x congruence to 1 modulo P or x congruence to what? Minus 1 modulo P. Okay. proof. Suppose x square congruent to 1 modulo p. So this gives p divides x square minus 1. That is same as p divides x plus 1 x minus 1. That is p divides either x plus 1 or p divides x minus 1. Since p is what? Prime. Since p is prime. Now p divides x plus 1. What does this give? This gives x congruent to minus 1 modulo p. Or p divides this one, means what? X congruent to 1 modulo p. So we get our required one as this one hold. So any one of these one. Now conversely, let x congruent to 1 modulo p or x congruent to what? Minus 1 modulo p. Minus 1 modulo p. Okay. Here also let me do a bracket. Minus 1 modulo p. So what does this give by definition of congruence? This gives p divides x minus 1 or p divides what? X plus 1. So that gives p divides x minus 1 into x plus 1. So this says p divides what? X square minus 1. So that gives x square congruent to 1 modulo p. Modulo p. Fine. This is about this lemma. Now next part we have to take the Wilson's theorem. Let me take that one in next video. Thank you.